C'est un très grand plaisir d'accueillir Thorsten Schumm ici. Thorsten est professeur à l'université, alors que je ne me trompe pas, Vienna Institute of Technology. Voilà, donc, pas mal de gens connaissent Thorsten ici parce qu'il a fait sa thèse en partie en France, au laboratoire Charles Fabry, avec Chris Westbrook. C'était une codirection entre Chris Westbrook et Jörg Schmidtmeyer. Et puis ensuite, il a pris un poste d'assistant professeur à Vienne. Et puis, il est full professeur depuis 2011, c'est ça?
Oui.
Voilà. Alors, la thèse de Thorsten, c'était sur des gaz d'atomes sur chip, des gaz unidimensionnels. Et il a continué d'ailleurs à travailler beaucoup avec Jörg Schmidtmeyer bien après avoir été recruté comme professeur à Vienne là-dessus. Ils ont des très très beaux résultats. Donc, j'aurais pu lui demander de venir parler vraiment de gaz indé, ça aurait été en lien avec le cours de cette année. Mais quand même, le grand œuvre de Thorsten de ces dernières années, c'est une horloge nucléaire. Alors quand je dis ces dernières années, j'ai vu que tu avais eu une RC sur ce sujet en 2009. Donc ça veut dire que tu penses à ça depuis quand même très longtemps.
J'ai presque fait ce que j'ai promis là-dedans.
Presque, voilà. Et comme quoi, il faut parfois attendre. Hein. Donc ça va bientôt faire 20 ans que Thorsten se passionne pour ce sujet, de trouver un moyen d'exciter des noyaux avec de la lumière. Et l'an dernier, eh bien voilà, le résultat a été publié. Je ne sais pas depuis quand est-ce qu'il a été observé, mais je sais qu'il a été publié l'an dernier. Et donc voilà, c'est je trouve personnellement un grand moment et je suis vraiment très content qu'il ait accepté de venir nous raconter ça ici.
Good. Well, it's a great pleasure to be here. I apologize for switching to English. My French has degraded over the last 15 years. If you ask questions, don't hesitate to do that in French. I'm able to understand and maybe even answer. Let's see. But the presentation will be in English. Yeah, there's not much to add. This is about efforts to laser excite or optically excite an atomic nucleus, and there is a finally in the title, which indicates that it's been a long struggle, not only personal for me, but this is a story that's about 50 years old. So yeah, it's really finally. We're happy that it's starting now. And I'm going to give you a little bit of a historical overview on when this started. And where we are now, and where I kind of believe this will lead in the years to come. Check. All right. So yeah, doing nuclear physics with a laser. This topic and this question is intrinsically related to one very specific nucleus. You may get the impression from now on we're going to laser excite nuclei all the time, like we do with atoms. That's not on the horizon. So there is one very particular nucleus which lends itself to laser excitation, which is the nucleus of thorium-229, which is a very specific, special isotope, and I will tell you a little bit about what it is, where it comes from, how much we have, or how little we have, actually. And then I'll tell a little bit about what one actually wants to laser excite or manipulate nuclear quantum states. And there's two stories that I will tell. One is the story of the nuclear clock, and the other one is how the nuclear transition relates to measurements of fundamental interaction constants of physics, in this case specifically the fine structure constant and the strong force interaction constant. And then comes a little bit of history, not so old history, how we learned about that there is one, and so far as we know, only one nucleus that has an excitation energy that is reachable with lasers or light, how we have learned about that over the years and decades. And then I'll tell you about recent experiments where we have actually succeeded to laser excite a nucleus and very rapidly increased precision and accuracy on quantities of this nucleus quite impressively. So somebody said we gain an order of magnitude in accuracy every 2 months at the moment, but I don't think that's going to stay on for forever. I'm here for you, so please don't hesitate to interrupt me at any point and ask questions. I have kind of stop points in the presentation, which shall encourage you to ask questions, because this brings together research from different directions of physics, and not the terminology may not be familiar to everybody. So please don't hesitate to ask if something is unclear, and then I'll try to say it again in different words or better, or find a way to solve that. All right, so the gap between atomic and nuclear physics. So on the left, you see the object that at least I and maybe many people in this room are kind of familiar and happy with, which is the atom, right? So there's a nucleus, there's electrons, and the quantum thing about it is that these electrons have discrete energy states. So I've drawn a rough energy scale. We're talking about something that is 1 to 10 electron volts. I'm not sure if electron volts is a unit that you are familiar with, but you don't have to. This is about optical energies, wavelength in the optical range, if you want. Okay. One important thing that will occur throughout this presentation is that these levels here, they are on the 1 to 10 electron volts in both in terms of binding energies and in terms of transition energy. So if I push in much more energy, I'll actually start ripping out electrons and start to ionize, so that we have to keep in mind that transition energies and binding energies are somewhat similar on the 1 to 10 electron volt scales. And over the decades, I can already say, we have learned to manipulate these quantum states, and we can do a lot of fantastic stuff with it. We can measure them very precisely, which is like the playground of atomic clocks. We can store information by putting these quantum states in qubit-like superpositions and build quantum computers and so on. So all of that, what we today call quantum technology, is more or less the toolkit we have developed to very precisely, accurately manipulate these electron quantum states in atoms or ions. Okay. Now, the part that when I started this I felt very uncomfortable with is nuclear physics. If I zoom on that object, well, by about 4 orders of magnitude, I again encounter a quantum object. So I can write down a many-body Schrödinger equation, and if I were able to do it, I could solve it and come up with energy eigenstates. So conceptually, it is a comparable object, but in terms of energy scales, it is very, very different. You see there's a capital M here, which indicates that these are mega electron volt binding and transition energies. Okay, so similar structure to some extent, but very different energies. And as a result of the difference in energy, the tools that are used by people that are interested in that object here and people that are interested in that object, they are very different. And often this is called nuclear physics, this is atomic physics. They're in separate parts of the buildings. People don't usually speak to each other very often. And so the crazy idea that me and a few others before me had is we have this fantastic toolbox of manipulating atomic electron quantum states. Wouldn't it be great if we could transfer at least some of that, and in particular maybe laser excitation, laser spectroscopy, into the nuclear world? And I just told you why that is a stupid idea. I just told you the energy scales don't match. We don't have mega electron volt lasers. And maybe we'll never have them, maybe we'll have them next year, but at the moment we don't. So there's a problem here. So then the work started, and the work is looking at the full isotope chart. The isotope chart, as far as we have accumulated, it has about 3,500 isotopes of all of the existing elements. There's a lot of isotopes. And you look at the energy structure of all of these isotopes, and you ask yourself the question, maybe among all of these 3,000-something isotopes, there are a few that have low excitation energies. So maybe there's like an exception. Maybe we can find something that actually is laser excitable. And here's the top, or the bottom 5, actually. So these are the 5 lowest excited nuclear states that we could find in the isotope chart. And then there's, at the very, very bottom, there is, as I already mentioned, the famous thorium-229, which has an excitation energy of about 8 eV. And me putting 8 eV there is actually already revealing a result which is about 3 years old. And I will tell you how little we actually knew about this energy for many, many years. But now we know it's about 8 eV, and for people that like to manipulate atoms or ions, this is 150 nanometer wavelength. So that's still kind of optical. It's, well, it's called vacuum ultraviolet, so it doesn't travel through air, but we can build lasers. There's a few groups on that planet that manage to build lasers at this wavelength, and we're actually using all of them at the moment. Good, okay, so thorium-229 is the one candidate, as far as we know, the only candidate which has a nuclear excited state that is maybe accessible to some of the techniques that we have established. So, and then comes my quantum physics thinking, oh man, that's a two-level system. We have a ground state, we have an excited state, there's an energy gap. Well, it's a large energy gap, it's about AdV, okay, and then there must be a lifetime. So I looked up what is the lifetime, and it turns out that the excited state lifetime is horrifically long. We're talking minutes to hours for an excited two-level quantum system. The excited state lives for minutes to hours. The reason is that this is a dipole forbidden transition. It's a so-called M1 magnetic dipole transition. That means it couples to the magnetic component of electromagnetic radiation, which, as we all know, is a weak coupling. So it's going to be very difficult to excite this nucleus. But okay, let's try. So if you try, you encounter a lot of difficulties. So everything about thorium is difficult. The first one is just having it, okay? So thorium-229, this specific isotope, has a lifetime of about 8,000 years. So if it had been formed when the Earth crust was formed, it has decayed ever since. There's nothing on that planet. So it doesn't exist. The only stuff we have is men and women made, and that is very rare. Unfortunately, it's more men-made in that case because it's remnants of the Manhattan Project. So the stuff that we use is stocks of uranium-233, which have been produced in the Manhattan Project, and uranium-233, you will see this in a minute, alpha decays to thorium-229 occasionally. So the overall amount of thorium-229 on this planet is below a gram, and the part that is usable and of sufficient purity for research is about 40 to 50 milligrams. Okay, so about scarcity, it's not easy to get, it's radioactive, there's a part here. The second complication arises from this energy scale. So 8 eV is ridiculously low for nuclear physics standards, but it's quite high for atomic physics standards, meaning if I build a light source at this energy and shoot at my atom, I will ionize it. I will have all kinds of excitations and reactions in the electron shell, which are fast and strong. So that means if I actually want my electromagnetic wave to penetrate and reach the nucleus, I have to make sure that I strip out the outermost electrons sufficiently so that I don't have electronic excitation channels, and I actually speak to the nucleus only. So what we will do in the work I'm presenting today is we're going to go for a 4+ thorium ion state. 4+ is radon-like noble gas configuration. It doesn't have electronically excited states, which are energetically accessible at 8 electron volts. I already mentioned that the interaction cross-section with light is low. It's significantly lower than any atomic or ionic cross-section. That means not only is it hard to produce 150 nanometers, also if you have a laser source, it's actually still very hard to excite this nucleus. Good, but there's a few pros why one should still maybe try. And the first one I already mentioned, it's essentially 1 over this quantity here, which is the spectroscopic line width. If I have a two-level system that lives for a time x, usually 1 over x is the Fourier limited line width. In that case, well, you can calculate yourself what is the line width of an excited state that lives for minutes to hours. It is very, very narrow, and this is why people are excited about using this as a reference transition for a new type of clock, which would then be a nuclear clock because it's relying on a nuclear transition. The second thing that is exciting, and I'm already raising something up, so the system we're talking about is this, right? So this is thorium-229 in a solid state environment. The great thing about this two-level system is it is sitting inside a nucleus, inside the electron shell, and actually this transition really doesn't care very much about the electronic environment that it's in. So that means I can do all kinds of nasty stuff to this atom or ion and still maintain the favorable properties of the nuclear transition. And when I mean nasty, I usually mean solid-state physics. In that case, we can actually implant these nuclei into transparent material and still do the spectroscopy. And this is exactly what we do. So we're going to do this in a crystal environment. And that brings about the idea that maybe we can actually build a nuclear clock which is solid-state based. The second point of interest, why people are interested in this, brings me back to this argument of transition energies and binding energies. And I'll tell you a little bit more about this in 2 slides. But it turns out that measuring this energy here very precisely gives you very direct access to, let's say, the forces that are constituting to this ground state and the isomer state, which are other than in electronic transitions, which is predominantly Coulomb, a competition between Coulomb repulsion of the protons and strong force interactions of all of the nucleons. So we have spectroscopic access to a wider range of fundamental interactions than we usually have in atoms or ions. All right, so 1 slide to the idea of a clock, 1 slide to the idea of varying fundamental or probing fundamental interactions. I'm not going to talk a lot about clocks. Just as a basic concept, a clock is usually some kind of stable frequency generator which drifts slowly and on a slow time scale is feedbacked on a quantum reference transition, which is usually some narrow spectroscopic line. And to identify whether a spectroscopy line is a good reference transition for clock building, we usually have a very simple expression, which is the Q factor, which divides the absolute transition frequencies by the line width. Narrow line width is good, high absolute transition frequency is good. And in that parameters, thorium performs fantastically because it's kind of the highest transition you can imagine. I said it's a very short wavelength laser, so this is a 2 petahertz transition we're talking about, right? So it's in the optical. The electromagnetic field oscillates 2 times 15 times per second. Very, very high transition frequency. And the line width, if it's true that it lives for minutes to hours, is going to be extremely narrow. Hence the idea of building a clock on this specific spectroscopy transition. If you look a little bit more into how to build clocks, because they are quantum objects, you have quantum projection noise and all kinds of other noise sources. And usually if there is noise, then you win with statistics, and winning with statistics usually works with a scaling of square root of number of interrogated oscillators, and that is the same here. And that also tells you high transition frequency is good, narrow line width is good, many particles is good. And solid state is many particles. That's the only message I would like to bring here. So the idea of putting all this into a solid state device is interesting also from a metrology perspective. And obviously, towards the end of the presentation, we're going to talk about how narrow it actually remains in the material, what are the effects, is there temperature, is there density, and so on. So we're going to come to that in case you already have that question, which naturally arises at that point. Okay, so that's the idea of building a solid-state version of a nuclear clock. What about fundamental constants? I keep insisting on the fact that what we are probing here, this 8 eV, is a kind of freakish coincidence of 2 bound state energies, but the bound states that are involved are bound states of mega electron volt total energy. So it takes 8 mega electron volts to actually rip out the neutron that is involved in that quantum transition. Okay, so the binding energy is huge, and just because of coincidence, I have 2 bound states in this nucleus, which are, like from nuclear physics perspective, degenerate in energy. For us, it's still a high energy for atomic physics standards, but for nuclear standards, it's the same, right? Because transition energies usually are hundreds of kilo electron volts. We're talking gamma energies, okay? This is more photon energy. In 2006, Victor Flambaum pointed out that because there is this discrepancy between the binding energy and the transition energy, there is an enhanced sensitivity to the energy scales which make up these binding energies, which, as I said before, is a combination of Coulomb repulsion and strong force interaction plus a few additional terms. I don't want to bore you with lots of nuclear physics, but if any of these two forces or interactions changes a tiny little bit, that produces a change on the MeV energy scale. So even a tiny change will, in absolute numbers, change a lot on this energy difference. I sometimes take the analogy, if I want to measure the temperature change of a stick, I better take a long stick, okay? If I have just a millimeter scale to measure it. So if I take a 100-meter stick, the effect will just be longer, and this is what's at the basis of this argument. Now, there is a lot of discussion how strong this sensitivity enhancement is, and there was a time around 2020 when about every 6 months there was a new theory paper predicting a different enhancement factor, and we're kind of come back to that a little later. But at this point, the main message is this: to some extent, by doing spectroscopy and precision physics, as we usually do it in atomic and molecular physics, gives us access to like the most fundamental processes happening in atomic nuclei. So I find that fascinating, that in tabletop laser spectroscopy experiment, you have access to strong force interaction. Usually you need other devices than a laser table and a few lasers to have access to this kind of energy scale. 2020, I said, Flambaum and collaborators were still contemplating about how is the transition frequency in the thorium-229 nucleus linked to fundamental interactions, and can it be used to measure variations of the fine structure constant or the strong force interaction constant. And they said, well, actually, we can't say unless we get an information from experiment. What we're looking is something that they call the quadrupole moment, and I'm going to tell a little bit more about what that is. It refers to a shape deformation of the nucleus. They need the information on the quadrupole moment to pin down this sensitivity factor. Then they use some theory because they don't have it. They use some theory to predict it, and they come up with a value that is minus 9,000. That would be 9,000 times more sensitive than any atomic or nuclear, atomic or ion transition clock or precision measurement. And I'm going to show you that this is wrong, not in order of magnitude, luckily, but in sign, because we did that measurement. Okay. And then there's another phrase that says that if we use this system, and if we reach a precision of 200 hertz on this nuclear transition, then we are as sensitive as the world record in looking for variation of fundamental constant in the fine structure, in variations of the fine structure constant. Okay, so that's kind of the target regime. So you get an order of magnitude. If we are able to do the spectroscopy on the, let's say, 100 hertz level, we're starting to be competitive. And you're going to see throughout this talk, we're about a few kilohertz at the moment, like about 1 year after it has been done for the first time ever, which is, I think, is an impressive progress. Are there questions on the introductory part of that presentation? There's one. Hi. Hey, Isabel. I hardly see you because I'm strongly illuminated.
You said that the nucleus is very insensitive to the electronic environment.
Yes.
But there is a hyperfine coupling with the nucleus.
So the insensitivity emerges from the fact that the nuclear moments are 3-4 orders of magnitude smaller than electron moments. The coupling to the same electric or magnetic field of an electron, just because the orbit of the electron is huge, it produces a lot of magnetism, and it couples to magnetism a lot, whereas the orbit there is small. So it's the smallness of the nuclear moments. It's not, and I insist on this, it's not a shielding effect by the electron shell. This is not the case. It's actually on the contrary. There's even a small amplification of surrounding fields transported to the position of the nucleus by the electron shell. But it's the smallness of nuclear moments which brings about the robustness. Any other question? Yeah?
I was wondering, was the value 8 electron volt found? Is it in a particle accelerator or is it some calculation?
Fantastic question. Just stay with me for another 5 slides. All right, there's one.
Very naive question. So what I understand in this structure that you're showing is that you have 2 levels and you're aiming for 1 photon processes, coupling these levels. Could one imagine configurations where you would have more levels and maybe have 2 photon or 3 photon processes?
You will have to bear with me for longer than him. Yes, is the short answer, very short answer. No, it's going to come. Okay, good. Then I maybe just continue. All right, good. So how do we know? How was it actually like kind of pinned down that there is a low energy excited state in thorium-229, and how low is low, and how did we actually get there, okay? And this has been done through what I call stochastic isomer population. So we, as a quantum physicist, we assume starting point is a 2-level system in the ground state, and we need to find a means to excite it to the first excited state. This is not what nuclear physics people do. Nuclear physics people look at nuclear decay, which automatically, stochastically, populates excited states of the daughter nucleus, for once it's a woman, the daughter nucleus structure, and then it relaxes to the ground state under the emission of gamma radiation. So this is why people observe nuclei and isotopes, because they send out characteristic gamma after nuclear decay. So we are going to look at nuclear physics methods for a few minutes and see how that has evolved over the years. Okay, so you're familiar with electronic states of atoms like S shell, P shell, and so on, the hydrogen atom. These are nuclear levels. They look similar, but all of these numbers are kilo electron volts. Okay, so that means excited states of thorium-229. There's one at 217 kilo electron volts. I don't even dare to calculate what the wavelength would be. So all of these are measured and known. Apart from that one here, which from a nuclear physics perspective has no interest at all because it cannot be measured because it is too low for the detectors that this community uses, which are usually like germanium single crystal detectors and so on. So over many, many years, they just put a delta there and say, and delta means small for nuclear physics, okay? Not much interesting. So how do we know? Well, we take, as I said, we take uranium-233 and just wait for it to decay. It alpha decays, it spits out 2 protons, 2 neutrons, and then it, with a certain branching ratio, populates all of the excited states. They live very, very shortly, picoseconds, nanoseconds, and then they decay to the ground state under the emission of characteristic gamma radiation. So all I have to do to measure all this is take a chunk of uranium-233, put it on a gamma detector, and look at the lines that are coming out, okay? And that's been done over 50, 60 years now. So this is why all of these states here are very, very well in databases and so on. So that is a way, and obviously there's a you see this here, there's a 2% branching probability that in a uranium decay, we end up in this low energy level state. So there is a population mechanism that doesn't rely on us actually knowing what this energy is, and we're going to use exactly this mechanism to start with. Now, based on this, I'm going to use the big one again. So if you look at these flashes, you see some of them end up in the first excited state, some of them end up in the ground state. So why not find pairs that kind of match up here? Take a few sums, make a few differences, and then we should be able to actually calculate by very simple arithmetics what this little gap here is, okay? And that's been done. This is exactly what's been done over the last 50 years. Whenever somebody, he or she, has a good or even better gamma detector than before, they put uranium-233, they remeasure these lines, and they come up with a prediction. What is this little energy range? Okay, here's the history. The history started in 1964. The first prediction was, we don't see anything, and the only explanation why we don't see this specific level is it must be so low that we can't see it, so it is below 100 eV. And that's known since a long time, and didn't bother anybody because, well, okay, nuclear physics doesn't really care about that. Then that experiment was repeated in the 90s, and they came up with a value, it's maybe 1 eV plus minus 4. So you have to look at these numbers with the mindset of ultimately I want to build a laser at that correct energy and build it. Okay, so 1 eV plus minus 4 is very difficult for laser builders. I can assure you that. So over the years, this number has changed. The error bars have changed. Also, there were new measurements on branching ratios. So they have refined this ever and ever again. Then for a long time, there was the belief it's 3.5 eV, which is right in the optical. That would be really fantastic. It would be easy and even cheap to build lasers that work on this, and many experiments were performed to actively excite this nucleus with light or see this photon here, because if it's populated spontaneously, well, this thing should just come out as a photon or gamma. So now you can make your choice whether you want to call something that is emitted by a nucleus a gamma, if you can accept the fact that you can have very low energy gammas. Okay, so that's you have to find yourself a way to call this thing that comes out, but it should come out spontaneously. People have measured it even. There's PRLs that say, oh, we have measured the gamma that comes out of thorium. It has been debunked. It wasn't true. Many experiments were in that range. Most of them were performed in liquid solution. Because that's usually what radiochemists do when they work with thorium. Usually they just put it in some liquid solution, and then they put this in front of a of a spectrometer and hope to see something. And then this field has come a little bit to a halt over some time. And then it was taken up again by it's actually technology development. So people have improved the gamma detectors enormously. And then at some point, I met a guy called Christian Enz, a professor in Heidelberg, that is an expert on X-ray. Actually, he's building X-ray cameras, so little pixels like this. So here's a 16 by 16 pixel set. So that all of these pixels, they are X-ray spectrometers. And so we decided to build a gamma detector in the energy range specifically for thorium. I'm not going to tell too much about this, but it's a fantastic device. It's actually a bolometer, so it measures the heat that is produced when a particle is absorbed. The heat changes the magnetic properties of these pixels, and then the change in magnetic properties is read out by a squid. Okay, so it's really transformed many times. Still, it is a fantastic device with an energy resolution of 10 eV for lines that are between 10 and 100 kilo electron volts. So it's really amazing device, at least for this energy range. Good. So we measured. We took uranium-233. We measured for many, because this thing is a thermal, so it has a count rate of 10 hertz because it has to cool down once it has absorbed a particle. So this is a very slow measurement. It took some weeks to do this, and then there is a spectrum that comes out, which is the spectrum of the excited states of thorium-229, and you see these are the low energy ranges, but it's still kilo electron volts. You see an x-axis and you think like, oh yeah, easy. You need to calibrate this thing. The problem is if you claim to build the world's best spectrometer, you have to calibrate it with not the world's best spectrometer, right? So we have to look up calibration lines here in the literature, and we did that extensively. So we look up the tables, the NIST database, whatever we could find to make a calibration. And the calibration looks great, right? So this is the signal amplitude, this is energy, and it looks super linear. Great, cool. So we take a fit, and we look what stays over. Oh, what stays over is curved. So we take a quadratic fit, and so on and so on. In the end, it turns out that if we take out one of these calibration points, the overall calibration of the device switches by 0.76 electron volts by one single calibration line. Okay, so that is the intrinsic calibration error of this device, and it's only related to, let's say, the fluctuations which are in the data sets that are available. So this spectrum here is online available. Whenever there's somebody who measures a calibration line with a better accuracy, we refit this and come up with a different arrow and then a different value for the isomer transition. Okay, anyways, so we take uranium-233, we look at some of the lines that come out. There's two that are about 29 keV. The second excited state of thorium-229 is at 29 kiloelectron volts. So there's these four states that come out. We measure these four lines. We make a subtraction. We come up with the energy of 8.1 plus minus 0.2 electron volts, which shifts the predicted energy from the optical into the vacuum ultraviolet. Okay, so if this is true, photons emitted from this low energy state here don't travel through air, through material like glass, through liquid. And that explains maybe why most of the experiments were not able to actually absorb something. Okay, so this shifted the transition energy into the vacuum ultraviolet range. Question at that point? Yes?
What would be the polarization of this gamma photon?
It's more or less randomly, so it's like spontaneous decay. It's randomly polarized because there's no alignment of the nuclei in these experiments. They're essentially embedded in metal. So we electrodeposit this. Okay, good. So, yes. That's Jakob, right? Right? Hi. Hi.
10 electron volts you mentioned. What was it? The uncertainty, the accuracy?
10 electron volts.
Resolution of that?
You mean this number?
No, before when you did about this, the detector that you're using.
Yes.
Before that? Yes, this here. Yeah, resolution 10 electron volts. So if the resolution is 10 electron volts, how can you get this 8 electron volt number?
Haha. Okay. That's not going away from my speak time. There is a certain level of noise rejection in this measurement, which is because we're not measuring one absolute line, but we are measuring energy differences in lines which are quite close together. So that means if the there's two answers to that question. The first one is we actually get a small error because we are measuring differences between transitions which are close by, so the overall calibration error doesn't hit us as hard. That is one answer. The second answer is the line width that we measure is as you see here, is 10.2 electron volts. But it's not uncommon that you can measure the line center better than the line width. Okay, so this refers to the resolution on a single. So if these two states here would lie apart by 15 eV, I would actually see a doublet in all of the transitions that lead to these states. Okay? I really don't see your face, so you have to make some clear. Yeah, that's that. Thank you. Great. Questions? No more questions. Good. So let's go back to this initial idea, is that this first excited state of thorium-229 is actually actively, to some extent, excited in nuclear decay. So all of that we would have to do is build a device that actually measures the decay from this delta state to the zero state. And that, as we now know, would be a photon. So we would just need to build a photon detector and put it in front of the uranium-233. That is a great idea. The problem is that the alpha decay of uranium-233 is an incredibly violent process. So what happens is that there is an alpha particle of 5 MeV energy ejected in the nuclear decay, and the freshly born thorium-229 daughter has a recoil energy of 86 kiloelectron-volts. So it's running through the material. I can't trap this in an ion trap or any other trapping technique. It's just a too high energy. So I have to do it in material. In the material, the freshly born thorium nucleus is rushing through the material. There's a lot of ionization. It's probably stripping most of its electrons and then gathering them as the particle slows down again. There's a lot of optical and X-ray background, okay? Per single alpha decay that populates this, I get about 10 to the 4 photons. And then I want to see the 1 when this ultimately comes down. And that doesn't work. So that would in principle be great, but we need a softer mechanism to populate this excited state. And that softer mechanism does exist. It's been suggested by Piet van Duppen in 2019. We should use beta decay. Beta decay is low in energy. The recoil that is pushed onto the freshly born thorium-229 nucleus is 2 electron volts in beta decay. So let's do all this with beta decay. That's cool. The only problem is that the mother you need to use is actinium-229 that only lives for an hour. I told you about something not being on that planet because it lives for 8,000 years. Well, this one lives for an hour, 62 minutes. It's even less on that planet unless you actively produce it. So we asked CERN, can you produce us actinium-229? And they said, yes, we can. Just means that nobody else can use CERN. So CERN was producing for 3 days actinium-229 for us and not doing collisions as they usually do. And I'm still very grateful they did that. So we did a very, very basic experiment. We produced an ion beam. We used the Isolde facility. That's a radioactive beam facility. Protons hammer on some foil. Fragments come out. These fragments are quadrupole mass filtered, and they filter out a beam that contains actinium-229. This beam with a 30 keV velocity travels, and it hits a target. In this case, we did place one of our crystals, just calcium fluoride, some VUV transparent material. We inject for half an hour. We turn this wheel over here, and this device here looks complicated, but it's really just a basic grating spectrometer in the vacuum ultraviolet. Okay, so we implant, we turn this in front of a spectrometer, and we hope for the VUV gamma to come out. And I did bet a lot of alcohol and lost on that wouldn't work. Luckily, I lost, so it actually worked. So we were able, together with the team of Piet van Duppen, to really see this axis now is not in electron volts or kilo electron volts anymore. This is now more familiar. This is the vacuum wavelength, okay? So it's really just a spectrometer, and in 3 different samples, we did see a peak at around 148 nanometers. So that means the nucleus is excited in beta decay. It decays to its ground state under the emission of the characteristic 8.4 electron volt gamma photon X-ray thingy. Okay? And since then we know pretty exactly what this energy is to a certain number of digits. And at that point we can start building a laser with reasonable chances of success. Okay? Good. Now that was short, so no questions here, right? Okay, good. Then we come to the real deal. Now we want to excite from the ground state to the excited state by a laser. And before we do that, I first have to explain you a little bit what this is. So first, we need a vacuum ultraviolet transparent material. 150 nanometer doesn't want to travel through material, really not. And so there is very few materials which are actually transparent in this material, in this wavelength range, and the only choice there is are fluoride single crystals. There is magnesium fluoride, there's calcium fluoride, there is lithium, aluminium, strontium fluoride, but it always ends with fluoride. It's so-called ionic crystals, and it's the most transparent material we have. So that means that the task was to embed thorium-229 into calcium fluoride, single crystals, okay? Not in a chemical way, but really by melting a crystal. So this is the calcium fluoride structure. Luckily for me, who is really not strong in solid-state physics, it's a very simple cubic lattice structure. And so every now and then we replace a thorium. We put a thorium where the calcium sits. I will show you in a slide how we do that. So it doesn't really change a lot in the crystal structure. However, they have similar ionic radius. However, thorium 4+, as I already said, wants to be 4+. It wants to get rid of its outermost 4 valence electrons. Calcium wants to give away 2. So this one actually has 2 extra electrons that we have to take care of. And there's a charge mechanism, a charge compensation mechanism that takes place in this crystal that puts in 2 additional fluoride ions to eat up these 2 electrons. Okay, so this is, you can imagine this as defect physics in solid states. This is the microscopic configuration we, to some extent, believe is taking place in that crystal. Now, how do we get thorium to replace calcium fluoride in these crystals? We can't put them with tweezers. We actually have to melt the whole thing and then just do crystal growing, right? Crystal growing takes place at 1,640 degrees centigrade. This is the temperature at which calcium fluoride melts, and then we do this. We take calcium fluoride. We drill a little hole here. You see this. There's a little hole here. And then we put thorium fluoride in there, and then we melt the whole thing, but not for the full volume, but only 2/3, and then we let it solidify again, and then we have the crystal structure, but we have thorium fluoride doped into this material. These are very small crystals because we have very little of this material. We have micrograms quantities, and we don't want to dilute this over a large volume because ultimately the laser will only go through a few cubic millimeters or less, so it doesn't really help us if we have a large crystal. Then the thorium will be sitting in corners where it produces background but no signal. So we have over the years, and that were many years, and it was very painful, still is, learned how to make these crystals really, really small to have a large concentration of thorium-229 nuclei in a specific volume. Good. We believe we have certain level of understanding about the microscopics. I already pointed that out, but that's all theory. But we've also performed a lot of characterization experiments. So solid state community is very advanced and developed in order. They have very advanced techniques to really probe the microscopics of constituents around this thorium. So we kind of believe we know what's happening in these materials. And then the experiment is stunningly simple. We run around with this crystal and ask, do you have a laser system at 150 nanometers? Do you have a laser system at 150 nanometers? And if somebody says yes, we say, okay, then let's do an experiment together. And the first group that answered yes was the PTB in Germany, a group of Eckehard Pike. They had built a dedicated laser system for thorium for years because Eckehard Pike is essentially the godfather of thorium-229 laser excitation. So he already had this experiment in his lab. So there's a large laser system. I love talking about lasers, but stunningly, not everybody shares my passion. So I'll try to keep it a little bit short. So it's a pulsed laser system that through a nonlinear process in a gas cell produces vacuum ultraviolet light, and his ambition was to have thorium-229 single ions trapped in a Paul trap and then laser excite these. Okay, and he had started building that setup, and the laser was already quite advanced. The Paul trap not so much, but I managed to convince him that the first thing we should do is actually shoot at my crystal, which we then did. Okay, so this is for all practical purposes. 150 nanometer or 148 nanometer tunable laser system with a line width of 10 gigahertz, and that is given by the pulse length. So it's essentially Fourier limited pulsed laser with a line width of 10 gigahertz. Okay, so this is the laser. Lasers, they all look like lasers. This is my team arriving with the crystal and detection stuff, and then real life happens. The doors are too small. We have to put things together that were not originally meant to be together, but we managed. We put our crystal and our chambers on their laser table. So you see, this is one of our tiny little crystals. There is a very fundamental detection system. So it's a large parabolic mirror that tries to capture a lot of fluorescence photons and project them on a photomultiplier. It's really not very sophisticated. There's some background filtering, but conceptually it's very, very easy. And then you see my team standing in front of the screen and waiting for the results to come in. And the experiment is, again, stunningly simple. You illuminate this crystal for 5 minutes at some wavelength. Then you turn off the laser, and then you wait for the photons to come out. I already mentioned that the lifetime of the excited state is minutes to hours, so you wait for quite a long time. And then if you don't see anything, you detune your laser in 10 gigahertz steps, and then you do the experiment again. And I see people laughing, which is fully justified. So you see people are still standing. After a few hours, they sat down, and then after a few days, they actually said, okay, we can do this remotely from home. It took a year. It took a year to do this experiment, to scan this laser finally over the uncertainty range we had, and ultimately, at some laser frequency, we shoot in and we get a response by the crystal. And then we have to verify that this is actually not a material response, but really a response from the nucleus. So here it is. We scan the laser back and forth, and eventually at some point, we see a line. Actually, we were impatient, so we didn't wait long enough for all of the excited nuclei to decay before we detuned the laser. So that means there is a hysteresis, so that depending on which direction we scan, there is a memory effect, and the line is slightly shifted. But if we are patient enough, then there is that dependence goes away. So that means ultimately we know the transition wavelength or frequency 2 gigahertz precision from that experiment, and here you see a lifetime. You see like a beautiful exponential decay. This is the photon signal of photons coming from the nucleus, and the lifetime is about 11 minutes. And I'm writing down in a crystal because I would like to remind you that a quantum two-level system, the spontaneous decay rate, changes if it's in a refractive index, which is exactly the case here. So there's a scaling of spontaneous decay with n to the third power, n being the refractive index of the material. The refractive index of calcium fluoride is something like 1.5 something. To the power of third makes a factor of 4. So this is actually already accelerated. 11 minutes is a factor of 4 accelerated compared to the decay that an isolated nucleus in vacuum would have. Okay? So we're actually lucky to be in this material and only have to wait for 10 minutes for the two-level system to decay to the ground state. And that, to our knowledge, is the first time that a nucleus was excited by laser. There was always this bad feeling nagging us that what if this is some defect, some color center in the material? It's unlikely because it's narrow line width, it has long lifetime. We did a test experiment where we did exactly the same but with the wrong thorium isotope. So we had a crystal that has thorium-233, which has a completely different nuclear structure that didn't respond, but still you don't really believe it. Luckily, 3 months later, a US group at UCLA repeated that experiment. They dialed in our number, but they had a different host material. They had a more complicated crystal, lithium, aluminum, strontium fluoride, and they find exactly the same wavelength to like a gigahertz precision. So that kind of verifies that this is not a material property, but really a nuclear result. Okay, so this kind of allows me to put like really a lot of specific numbers. Now you see we know the wavelength. You remember the starting point was below 100 eV. Then it was like 1 ± 4. Now we're starting to have significant numbers of digits on this transition frequency. It's a 2 petahertz transition frequency or 148 nanometers, and we have a lifetime measurement. Good. So it's a two-level system. We could end here and say now it's under control. What can you do with it? We have mapped out everything. But now comes your question, I think. Now comes your question, which is it really, is that the whole story? Is not something happening inside this crystal? What is the coupling to the environment? And so on. So we pushed this a little bit further and used a much finer laser system. So this one was 10 gigahertz. Now we are We're using a laser now that has about 10 kilohertz a line width. That is a different laser, and again, if you want to ask me about lasers, you will make me very happy, but I'm not going to speak a lot about it. So there's a little piece of our crystal here. It's actually the same crystal that is a part of the same crystal, cut down from the same crystal that was used at the PTB experiment. This now is in Junyi's experiments in Gila in Boulder, Colorado. So you see the laser goes through. There's again a very basic detection system looking at fluorescence photons. I spare you the laser details. There are special papers in case you're interested. This is a frequency comb, so it's actually not a single line CW laser. It is a pulsed laser, but it's so pulsed that it produces a comb structure, which you can imagine as many individual CW lines. Okay, so we're not scanning a single line across the nuclear transition, but we're scanning an entire comb, and so there are many occasions for resonances. But we can deconvolute that. That's a known technique. Okay, so we did scan again with this laser over the nuclear transition, and to our, well, I hope at least to your surprise, not to mine, because I hoped that would happen, we see more than one line. We don't see a two-level system. We see, well, you see there's absolutely 4, maybe there's 2 additional lines here. What could that be? Maybe a word on how we have improved. So this is 4 months later after the first laser excitation was published. This is 4 months later. We are now working at 100 to 10 kilohertz resolution. So that means we now really have a lot of significant digits on this number. So if I tell this to nuclear physicists, we know just one, but at least one nuclear state to 10, 11 digits in energy. They don't believe me. Okay, good. And so at the moment, and I'm trying to, you remember in that paper it says we need 200 hertz in order to be competitive with current searches for fine structure variation. At the moment we're at 5 kilohertz, so not so far away at all. The good thing about Junyi's laser system in Boulder is that it's automatically linked to one of the world's best atomic clocks, the strontium clock. So we actually have performed a comparison measurement of the thorium with the strontium clock. And that was, again, published quite nicely. So what about these lines? Now, I tried to tell you that we have some level of understanding about how the microscopics of this crystal, of this thorium inside the crystal look like. I said there's these 2 additional fluorides and so on. These surroundings produce an electric field and an electric field gradient at the position of the nucleus. The nucleus itself looks like an American football. It's not a circle, it is elongated. And that means the proton distribution is not spherically symmetric, which leads to the fact that there is an electric quadrupole field. And that means an electric quadrupole field interacts with an electric field gradient of the surrounding crystal, and that means the ground state, this is the nuclear ground state, this is the nuclear excited state, there is a quadrupole splitting. That's a known effect in nuclear physics. Due to the interaction with the crystal matrix fields, there is a quadrupole splitting. The ground state splits into 3 levels, the excited state splits into 2 levels, which makes 6 possible transitions. One of them is forbidden. The 5-half, 1/2 here, this one is forbidden. The others are observed. And that explains the lines we have seen. And now it comes the moment when we can actually use precision laser spectroscopy to learn something about nuclear physics, because from these numbers, these level splittings here are determined by the electric field gradient in the material and the nuclear quadrupole moment, okay? And there are 5 lines. This system is mathematically overdetermined, so we can actually extract all of these numbers. So we can extract the nuclear quadrupole moment. We can even extract the change of nuclear quadrupole moment, which refers to a change in deformation of the nucleus when it goes from the ground state to the first excited state, which is on the 2% level, but with the accuracy we now have, we can do this. So this is looking at nuclear parameters, and this is exactly the nuclear parameter that was missing in the theoretical models for Victor Flambaum in order to determine this enhancement sensitivity parameter that determines how easy or hard it will be to measure variations of fundamental constants by looking at this energy very precisely. So we've been able to do that in collaboration with June, Mariana Sofranova, and my team, and we turn out that the factor is about 6,000, which is same order of magnitude as what Victor predicted, but has a different sign, actually. So that's nice. We can actually do reasonably interesting nuclear physics experiments doing laser spectroscopy. The second aspect is we can also learn something about the surrounding of the nucleus, which in this case is the electric field gradient. So we can measure the electric field gradient. There is a deformation. I spare you the details, but it also means to some extent all of these lines that we observe in the material. Now comes the question, is this actually a good system for a clock? All of these material parameters depend also, all the position of these lines depend on these material parameters. That means if I use a different crystal, the lines will be different. And not even that, if I use the same crystal at a different temperature, the lattice will shrink or grow a little bit with temperature. These parameters will change, and that means my clock transition is temperature dependent. That's not as shocking as it may sound, because that's also the case in atomic physics or ion physics. But let's have a look at this. So we looked at these lines as a function of temperature. The good thing about this thing is it's very easy to change the temperature. Just put a Peltier or just some cryogenic cooling. So we changed that over a factor of 100 Kelvin. And we looked at how these lines move. This is in megahertz, okay? You see there's so for about 100 Kelvin change in energy, the transition lines, they move on the order of 2 megahertz. There is one that hardly moves at all, which is quite interesting for clock operation. That's an effect because there is a quadrupole interaction, which I tried to explain, which is this splitting here. There's another shift, which is the so-called isomer shift, and for this specific transition, these two go in opposite direction and kind of cancel each other. So this might be an interesting transition to use for a nuclear clock, and that was actually published this Monday. Right, so that is the current state, and if you give me 3 more minutes, I'm going to tell you what we think we will be doing this year. Okay, I see yeses, and I hear yeses and see noddings, great. So there's 3 things I would like to inform you about or tell you about. So the first thing is I said there is the exponential decay of the thorium-229 in a specific material. It depends on refractive index, but otherwise it's kind of unperturbed. So it's the free photons that are raining out of this on an exponential decay. Turns out that we can manipulate the excited state lifetime by offering the system an electronic decay path. You can imagine the excited state nucleus like a little spring. It has a lot of energy and it wants to get rid of this energy, but it can't because there are no electronically states available that are energetically allowed that it can give this energy to. But we can bring electronic states into resonance by laser exciting something some defect in the material, and all of a sudden the nucleus sees, oh, okay, I can give my photon energy in that direction, and then there's a radiative or non-radiative process that we don't know yet that accelerates this decay. We call this quenching. Okay, so we can laser excite the nucleus, and then the spontaneous decay starts. But then we shine in a laser here. We've also done it with X-rays, but laser is simpler. And then that actually accelerates the decay, and when we turn off the laser, it falls back to the 11 minutes lifetime. Okay? We call this quenching, and we first thought like, oh, we have to excite electrons above band gap for this to happen. Turns out the blue laser pointer does the trick. And we don't know why yet. And so that's something we're gonna investigate a little more, because it's actually quite exciting, and it allows us to speed up these experiments, because if I ever want to build a clock that relies on a feedback cycle, having to wait for 11 minutes to see whether my excitation attempt has been successful and then I have to start over again. If I have something that allows me to quench down the isomer to the ground state to reinitialize the system faster, that's actually good for clock operation. So we're looking into this quenching effect and to understand what's happening there. The second thing is, I said I love lasers, but 148 nanometers is really not a good wavelength to work with. At the moment, what we're doing is we're resonantly exciting from the ground state to the first excited state in a 1-photon transition. What we would like to do is to do this in a 2-photon transition, where both of the photons would be at least below 200 nanometers, because then they would travel in air, which would make building a laser table with light that doesn't travel in air is really not fun. So we try to avoid this by playing with 2-photon excitation schemes. The last thing I would like to show is I showed you this quadrupole structure, and we're currently probing these transitions optically. And I said these are 2 petahertz transitions. These splittings here are on the 200 to 300 megahertz level. This is radio frequency. That's simple. We could just play with these levels by putting a coil around that and drive these transitions here, and then we would maybe have some sort of a non-optical readout scheme that could also help us to maybe speed up the system. This is a known technology. It's called nuclear quadrupole resonance. You essentially, you apply a radio frequency and then you flip the spins and you hope to get a macroscopic magnetization that oscillates that you can read out in order to probe these levels here. And we started seeing a first signal on that. That's a non-optical experiment. That's really just a crystal in a coil in a cryostat. All right. I think it's obvious, but I would like to point it out that none of this was done by me alone. But all of that happened in a lot of collaborations with the team that works at Isolde, with the PTB team, the GILA team, and many people that I probably forgot. So I would like to acknowledge the great work that all of these have done over many, many years, and that without them that wouldn't have been possible. And that is your last chance to ask questions.